Swayam Prabha. Digital India. Educated India.
Good morning. Last time in the lecture we saw how to use the force method to solve a truss analysis problem. Just to quickly review that process, if you look at what we looked at, this was the truss example that we looked at, and it was a 4-panel truss. This was the loading, and we calculated the forces in the members due to the loading. For that, we took x1 and x2 as the two redundants, and then we went ahead and found out the forces in the base structure, that is without these two both being 0. We found out all the forces in all the members. Then we applied x1 equal to 1 and x2 equal to 0, found out the forces, applied x2 equal to 1, x1 equal to 0, and found out the forces. And after that, we put all of those values that we computed in one table, and then from there, from the table, we computed all these various parameters, and ultimately these were the two equations that we got, and we solved for x1 and x2. And once you solve for x1 and x2, then you know what the values are in those parameters, and you can find out all the forces. Today what we are going to be doing is we are going to be looking at the second part of the problem which we didn't solve, which was forces in members due to the temperature only, where AB, BC, CD, DE are subjected to an elevated temperature of 25 degrees, where alpha is 1.2 into 10 to the power of minus 5. So today we are going to be looking at how to do this particular problem. Okay. Note that this remains as our x1 equal to 1 and x2 equal to 1. These are still our virtual force and real force systems depending on how you are going to be using them. I've already talked about them last time. I'm not going to repeat that. So now the only thing that happens differently is that only change that happens is that these equations, if you look at this, and there's also another equation here which I did not write it down that day, that is 1 upon EA PI P2I Li. Note that this term is just replaced by, what is this term? This term, if you look at it, is nothing but the deformation, real deformation in I member because of the loading. Okay. Now in the case where we have the temperature problem, in the temperature problem, all that happens is you calculate the deformation in the member directly. Calculate the deformation in the member directly. So you don't calculate forces, you calculate the deformation directly, and your problem statement becomes this way. Delta 1, 0 is equal to summation over all the members delta I into P1I, and delta 2, 0 is equal to I delta I P2I. These come from your virtual force equations. I don't want to go into that all over again. This is the only difference. The computing of F11, F22, F12 and F21, which I looked at last time, which are essentially, if you look at it, these remain the same. Only this and this for loading is this, and when you have temperature, this is different, and this is given by these, where these are the temperature deformations that you get in every member. Okay, so let us look at it. We have only member AB, member BC, member CD, and member DE. These are the only members that are subjected to the elevated temperature. So let us find out delta of AB due to the elevated temperature. How will we find that out? Alpha. So alpha is 1.2 into 10 to the power of minus 5 into delta T. Delta T is 25 degrees into L. What is LAB? LAB is equal to 5 root 2. Okay, so if you look at this, what does this become? This becomes 1.2 into 2.5 is 30, 30 into 5 is 150. So this becomes 1.5 root 2 into 10 to the power of minus 3 meters. Okay. So then similarly delta BC, if you look at it, is 1.2 into 10 to the power of minus 5 into 25 into its length, which is 5. So this is equal to 1.5 into 10 to the power of minus 3 meters. Delta CD similarly will turn out to be 1.5 into 10 to the power of me, and delta DE will turn out to be 1.5 into 10 to the power of minus 3 meters. So we have computed these. Now these are the only ones. So here all that will happen is delta 1, 0 will only have delta AB into the P1 of AB, and P1 of AB we have P1 of AB is 0. Okay. Then we have delta BC, which is 1.5 into P1 BC. Then delta CD into P1 AC, and delta DE is into this. So if you look at it, if you look at the entire procedure, since P1 AB, P1 CD and P1 DE are all 0, the only thing that contributes is BC, and so delta 1, 0 will turn out to be equal to 1.5 root 2 into 10 to the power of minus 3 multiplied by 1 by root 2 minus, because it's minus 1 over root 2. So delta 1 basically becomes minus 1.5 into 10 to the power of minus 3 meters, which is 1.5 millimeter. Okay. Similarly, we can compute, and here again for P2i, you will see that only CD comes in, and CD has exactly the same concept. And therefore, if you look at it, that you will see, sorry, I have made a mistake here. Delta BC is not 1.5, it is, so you basically have 1.5 over root 2, so 1.5 over root 2, that's approximately about a millimeter. Similarly, delta 20 also turns out to be exactly the same by computing, in that case, CD, so it will be 1.5 into 10 to the power of minus 3 multiplied by minus 1 over root 2, it becomes minus 1 over half. So essentially, once we have computed delta 10 and delta 20, we substitute the same equations that you have, which is delta 10 plus F11 x1 plus F12 x2 is equal to 0, delta 20 plus F21 x1 plus F22 x2 is equal to 0. And since we know these, and these, we can solve for x1 and x2, and the value of x1 and x2 turn out to be equal to plus 17.6, and so is x2. (17.6 kilonewtons). And once you know this thing, and then the force in the member is going to be equal to P. Now in this case, what is P? P is the load due to the temperature alone. So temperature alone, this is 0. So you're going to have P1 I, that is the force in the member, into x1 plus P2I into x2. So this becomes the force in all the members due to temperature, where P1I and P2I are already, we've got, these are P1I and P2I, okay, P1I and P2I, and you know x1 and x2, and you can obtain the forces. So this, in a sense, is your the forces that you find out in your truss for temperature. Okay. So now what we want to do is we want to go ahead and look at a frame problem. We've already looked at how to tackle a realistic truss problem, and today what I'm going to be doing is I'm going to be looking at how to treat a frame problem, and I'll take an actual problem and go through all the numbers, so that at the end of it all, it helps you to be able to solve a frame problem too. So let us take a frame and I'm going to take a simple frame. See, essentially, if you understand the concepts with a simple frame, you should be able to use it to solve any problem. So I'm going to but I'll go through all the details so that you know how to tackle the problem. Okay. So let us take a situation where we have, this is 5 meters, this is 5 meters, and let me call this A, B, C, and D. And these are the loads on the structure. This is acting at the center span, so it's like 2.5 meters. And this is acting at B, a lateral load. This is a typical kind of load you'd have, a gravity load and a lateral load due to wind or maybe even earthquake, it doesn't matter. So this is the load, and this we have to draw the bending moment diagram. for this particular structure. Remember, I'm going to explicitly state it that we only consider flexion. In other words, both axial and shear deformations are neglected. Okay? So this is the problem. How many degrees of static indeterminacy? I'll leave it up to you to go through your steps. Using my procedure, you will see that the static indeterminacy is 1. And I'm going to take this reaction as my x1. Okay? So this is the problem statement. So now I need to go, what's the first step? The first step is find out the, take the base structure where x1 is equal to 0, find out all the forces in the member and find out the deformations, and then put x1 equal to 1 and find out the bending moment diagram. And once you get the bending moment diagram, you can then, well, go through the process. Okay, let's go through this particular process. So the first part is where x1 is equal to 0. Okay, let me put it explicitly, x1 equal to 0, and this is the loading, this is 10, 10. So what will be the reactions at this point? Reaction over here will be 10, reaction, horizontal reaction will be 10, and you will see that this gives rise, look, this is 5 meters and this is 2.5 meters, 2.5 meters. So if you look at this, 5 into 10, if I take moments about this point, 5 into 10 plus 2.5 into 10, and that is the net moment that has to be resisted here. So you have a resisting moment here equal to 75. And once you have that, you can draw the bending moment diagram. Let's see how I'll draw the bending moment diagram. The bending moment diagram over here would land up being starting from C. Okay, the value over here would be 25, and then that would be the same value here. Okay, and then this becomes 75. The sense of the bending is this way, and the sense of the bending over here is this way. Okay, this is your bending moment diagram, M diagram. This is M diagram for x1 equal to 0. So this is the base structure bending moment diagram. Okay, note that I have also made the assumption that this EI and this EI are the same. So actually, if I just divide by EI and EI, that would give me my M by EI diagram. What is then this? What is the M by EI? This is the curvature. So it directly gives the curvature diagram for the real curvatures under the loads. Okay. What is the next step? Next step is for x1 equal to 1. So let us find out what the reactions at this point are. The reaction at this point is going to be 1, this is going to be 0, and what else? What's the moment going to be equal to? See, this is 5 and this is 5. So if you look at it, take moments about this point, this gives rise to this, so you're going to have a moment in this direction which is equal to 5. Well, I'm not going to write kilonewtons because this is just unit, there's no force. So this is the moment, 5. Okay? And how will the bending moment diagram look? Note, I don't care which direction I draw the diagram, as long as I show the sense. I am drawing it in the same direction as that, but note that here the bending is hogging. In other words, tension at the bottom, compression at the top. Here it's sagging, so it's going to be tension at the top and, sorry, just the opposite. This is sagging because tension at the bottom, so it's going to be sagging, okay? And this is going to be hogging. So although I've drawn it on the same side, you can draw it on the other side. I don't, it doesn't really matter. You can draw it however you have been asked to draw. So I think, as long as you're consistent, this is the point that I always make, that as long as you're consistent, it does not matter. And this value is equal to 5. And you will see that at this point, it's going to give rise to a sagging moment. We have to. It is actually this way. And that is correct, that if you look at this, you'll get it over here. Here, it's actually the opposite way here. If you look at this, this is this way, and this way. This is the opposite way. Okay, I'm so sorry, made a mistake here. Please ensure that you understand. This is hogging. This is hogging because this creates a curvature in this direction, and that is what you're doing here. And this also is this way. Okay? So, and over here, you have it as sagging. This is sagging. Okay? So what do we have? Let me just put it together in another one. I'll draw it small so that I have both of them. The actual M by EI diagram is starting from C. This is hogging, 25, 75. These are kilonewton meter because the loading is kilonewton and the forces are. So these are 25 by EI and 75 by EI. Note that if you have two different EIs, then the moment diagram and the M by EI diagram would not be the same. But in this case, I've taken them to be the same, and this is the small M1 diagram. The M1 diagram is, I've shown it on the same side, but this one is, the sense is opposite. Okay. So this is the M by EI diagram, this is the M1 diagram. Now what do we do? Well, we already seen that. Note that if I want to find out the displacement at this point, then my equation becomes delta 1 0 is equal to integral over the whole length M1 into M upon EI dx over the entire length of the frame. Okay? So that is delta 1 0. So if we take this, if you look at this particular situation, then all you have to do is take this area and at its centroid find out this value, take this area and the centroid find out this value. So if we do that, I'll go through the steps, right? So let us look at it. What will you get over here? This particular one, what is the area under the curve? 25 upon EI multiplied by 2.5 by 2. That's the area under this curve multiplied by, now let us look at this. Which point would this be? This point would be 2.5 by 3 from this end, which is actually 5 by 6. So if you look at this, since this is 5, okay, this is 5 by 6 from this point. So if you take that, you will see that the value at that particular point, the centroid of this graph, is going to be equal to 25 by 6 is going to be the value at that particular point. Is that clear? So it's going to be equal to 25 upon EI multiplied by 2.5 by 2, this is the area of this curve, multiplied by 25.6, which is the value at the centroid of this. This is the integral of this area, okay, the integration over this length. Then we look at it over this length. This can be broken up into two parts. One, a rectangle of 25 by EI. So you're going to have plus 25 upon EI into 5, that is the area under this curve, multiplied by the value at, that's going to be 5, because this is a constant. It doesn't matter where the centroid is, it's going to be the same. And the next one is going to be the difference, which is 50 upon EI. So 50 upon EI multiplied by 5 divided by 2, this is the area of this triangle, multiplied by 5, which is the centroid at that point. If we look at all of this, what we get is 1380 upon 2 EI. So this is delta 1, 0. This is the value of delta 1, 0, and then we need to find out the deflection due to x1 equal to 1. What is the deflection due to x1 equal to 1? That is my F11, that is my flexibility. Displacement at 1 due to unit load at 1, and that is equal to m1 squared upon EI dx. Okay. If you look at this, this is, what is the flexibility? Flexibility is displacement at 1 due to x1 equal to 1. So what is going to be the actual displacement due to x1? It's going to be F11 into x1. I'm introducing the concept of flexibility which I've introduced with the truss. I'm doing the same thing over here. So if you look at this, if I draw this, and this will then be this integral with itself upon EI. Okay. So if you look at this, this is going to be equal to 5 into 5 by 2, that's the area under the curve, multiplied by 10 by 3, that is the value at the centroid. Okay. Then plus 5, sorry, this is going to be 5 upon EI because this is the real part, and then 5 upon EI multiplied by 5 multiplied by 5. What are these? This is the integral of m1 squared dx over this length, and this part is the integral over this length. Okay. So if we look at this, this is going to be equal to 500 by 3 EI. Okay. And so this is my F11, and so what is my compatibility condition? Delta 1, 0 plus F11 x1 is equal to 0. Since there is only one redundant, this is the only additional equation that I require, and from this, by plugging in the value of delta 1, 0 and F11, I get x1 is equal to minus, no, I'm sorry, I have made a mistake. I just wanted to make a point here that since this and these are opposite, the delta 1, 0 turns out to be negative 1382. So here x1 equals to 8.283 kilonewton. So I have got the value of the reaction at the support D that we have. Now once I have got that, what's the next step? The next step here is to actually draw the bending moment diagram. However, before drawing the bending moment diagram, let me draw this is my loading. Now I know this value, right? This reaction. So this is A, this is B, this is C and D. I found out this reaction, and this reaction value is 8.28 kilonewtons. Now once I know this, I can actually find out the reactions at this point. This reaction is going to be 1.72 kilonewtons. This is going to remain 10 kilonewtons, and what I get is that if I find out that the moment over here is 10 into 5 plus 2.5 into 10, that's 75, minus 8.28 into 5. So this is going to give me a moment in this direction whose value is going to be equal to 33.60 kilonewton meter. So once I have found out the reactions, I can proceed to finding out the forces in the bending moment diagram. Let me just see how will I draw the bending moment diagram. Let me go piece by piece. Let me go in this particular case. So I'll take BCD, I'll separate out BCD and AB separately. So if I do separate out, then what are the things that I generate? If I take out BCD, okay, this is 8.28, this is 10. Note that I'm going to isolate the joint, and then I'm going to have the member. So this is A, B, C and D. The only difference is this cut that I have made is actually infinitesimally small. It's just so that I can isolate the joint B and look at its separately. So now this one, when I make a cut here, what are the forces that I generate over here? The forces that I generate over here are a shear. Okay, so the shear is going to be in this direction. Then a moment. Okay, the moment, let us just take positive moment right now. So the positive moment will be in this direction. And what else? There could be an axial force too. Note that you don't have to consider shear deformations and axial deformations, but the forces are still going to be there. So this is going to be M, this is going to be V, this is going to be P. And can I find out these values? Sure, because I have this. Here I know this is a roller support, so moment is going to be equal to 0. So what is V going to be equal to in this particular case? V is going to be equal to 1.72, because you take sigma Fy, you will see that it's equal to 1.72 kilonewtons. What's the moment over here? Well, let's see. Let's take moment about this point. This is going to give you 10 into 2.5 this way, and this is going to give you 8.28 into 5 the other way. So this is going to give you 41.4 minus 25. What is that going to be equal to? It's going to be equal to 16.4. Which direction? If it's going to be, actually if you look at it, this is going to be this way, this is going to be this way. So the net moment is actually going to be, if I'm showing this way, it's going to be minus 16.4 kilonewton. What can we say about P? Take sigma Fx equal to 0, you will see it's 0 kilonewtons. So I found out the forces here. Once I find out the forces here, just the opposite ones are going to be coming here. Now let me take this one. This one, I know all the reactions that are coming here. 1.72, this is going to be 10, and we've already found this out, right? So this is 33.60 kilonewton meter. Okay, and if you look at this particular case, so how do I find out the so when I make a cut here, I'm going to get a reaction V here, I'm going to get a moment here, and I'm going to get an axial force P here. So let me just see, this is, I'll make them separate so that the P prime. So what will be P prime equal to sigma Fy equal to 0 gives me that P prime is equal to 1.72 kilonewton meter. What is V prime going to be equal to? If you look at this, sigma Fx equal to 0 will give me 10 kilonewton meter. And what is M prime going to be equal to? Let's see. 10 into 50 is going to be in this way. Okay, 33 is in this way. So what is it going to be equal to? If you look at this, this is going to be giving this way. Okay, so if you look at your moment, it's going to remain, this moment is going to be equal to 50 minus 33, so that's going to be 16.4. So let us look at this, review this again. Taking moments about this point, what do we generate? We generate that this moment plus this moment is equal to this moment. So let us see, M is M plus 10 into 2.5 minus 8.28 into 5 is equal to 0. That is sigma M equal to 0. If you take that, you will see that this is going to be plus 16.4. Okay, and this is the, if you take V plus 8.25 minus 10 is equal to 0. So V is going to be equal to this, and sigma Fx equal to 0 is going to give me P equal to 0 here. In this particular case, what do you get? If you take sigma Fy equal to 0, you will get P minus 1.72 is equal to 0, so you get P. V prime, you get V prime minus 10 is equal to 0, so you get V prime. And similarly, moment plus 33.60 minus 10 into 5 is going to be equal to 0, so moment is going to be equal to this. Okay, so I have found out the at the ends of the two members. So now, and similarly, I can actually find out the forces at the joints also. Let us look at that. Okay, so I'm going to spend some time looking at equilibrium here, because after this I am not going to be looking at equilibrium. So now I have already done this, so I'm just going to put them down. .28 kilonewton here, 1.72 kilonewton, load 10 kilonewton, moment over here is 16.4 kilonewton meter. What else? Over here I have 1.72 kilonewtons, this is going to be 10 kilonewtons. Moment over here is 33.6 kilonewton meter. At this point, I have 10, I have 1.72, and I have moment equal to 16.4 kilonewton meter. So now let us do it on this side. So this side is going to give rise to this force, which is going to be equal to 1.72, is going to give rise to a moment here. Okay, So, and here I have the 10 kilonewton force, and then over here I'm going to have 1.72. This is going to be in this direction 10, and the bending moment is going to be in this direction. So let us look at the joint now. Let us look at the equilibrium of the joint. Let me take of equilibrium of the joint, sigma fx equal to 0. I have minus 10 here, so I'll put it minus 10. I have plus 10 here, plus 10. That's it. There's no other force here, so this is equal to 0. Automatically satisfied. Then we look at sigma fy equal to 0. Sigma fy equal to 0 is going to give me that this is upwards 1.72. There's no load over here, and over here it's downwards 1.72, so it's 0. Check. And then let me take moment equal to 0. Let me take moments about this point. Since these distances are 0, these do not give rise to any moments. So what's the moment? I have a clockwise moment here, an anti-clockwise moment. The clockwise moment is 16.4. The anti-clockwise moment is 16.4. So check. So that means all that I have done is correct. And so now, once I have this particular loading done, now the next thing that I'm going to be doing is I'm going to be actually putting together the bending moment diagram. Okay. So now, since I know all of those, how will the bending moment diagram look? This side remains the same. It's going to be 16.4, 33.6. So AB, there is no mistake. It is 33.6, and this is 16.4. This is also 16.4. Okay, this is this way. And let's see what we have. You see, let's see what the moment at this point is going to be. Moment at this point. If I take a cut here. So I'm taking a cut exactly to the left of this load. What is going to be the moment? There's going to be 16.4 and this. So take moment about this point. It's going to be 16.4 plus 1.72 into 2.5. So that is going to be equal to so this is going to go this way. So this, if you look at it, is going to be equal to 20. This is going to be 41.6, so it's going to be 20.8. So this value is going to be 20.8. This is going to be 16.4. All of them are in kilonewton meter. So this is the bending moment diagram for the actual structure, where I have included both the effect of the actual loads as well as the redundant force. So this, in essence, is my force method solution. I hope that with this kind of procedure, and I have gone through a detailed frame analysis problem so that you know exactly how the force method is used to solve a frame problem. Till now I have always been talking about the basics. So this time I have gone through all the details so that you can actually feel comfortable using the force method for solving a frame problem. Okay. So now, just to refresh your memory, up till now all that I had done was going to be a review. You've already hopefully used the force method, etc., for solving both truss as well as beam and frame problems. Okay, so let me just go back and say, in essence, what the force method entails. This is irrespective of whether you have a truss or beam frame. In a beam frame, the only thing that happens in a frame, if you notice, the only difference between a beam and a frame that I pointed out that day was that in a frame, all that happens is what is shear over here becomes axial force over here, and whatever is shear over here may become axial force here. It would have if this had not been there. So the point that the only difference between a beam and a frame is that in a beam, if you have multi-span beams, a shear in one beam will always be a shear in another beam. An axial force in one beam would be an axial force in another beam. But in a frame, a beam and a column, okay, the forces, the shear forces in the beam may land up giving axial forces in the column, and the shear forces in the column may land up being axial forces in the beam. That is all that is there. Otherwise, equilibrium and all the forces that you develop are identical whether you have a beam or a frame. Okay, so that's the reason why I have the equilibrium considerations may be different in a beam and a frame, but as far as the solution is concerned, there is no difference between a beam and a frame, and you only consider flexure. And in a truss, you only consider axial. Okay. So what does the force method entail? The force method entails, 1, find static indeterminacy. This is fundamental to using the force method. If by now you do not have confidence in obtaining the static indeterminacy of structure, there is no way you are going to be able to use the force method. So please, given any structure, you should be able to find out the static indeterminacy of the structure. I have spent the first 2 lectures looking at how to determine the static indeterminacy for a truss as well as a beam frame structure. So by now you should be able to get the static indeterminacy. If you can't, please go back, look at enough problems, look at any book on structural analysis. Take up some problems, essentially structural analysis of statically indeterminate structures. Take up any structure and find out the static indeterminacy. If you are confident that you found out the static indeterminacy properly, you can use the force method easily. So find the static indeterminacy. Once you find the static indeterminacy, you identify the redundant forces. What are the redundant forces? Those are the forces on the structure. They could be a support reaction, they could be internal forces. If you looked at the frame problem that we looked at, we took the support to be a redundant force. If you looked at the truss problem that we solved, we took internal forces to be redundant forces. It is not, the only thing is that redundant forces have to be such that if they were 0, the structure would still remain stable. That is most important. You cannot take out redundant forces, put something equal to 0, which will make the structure unstable. That cannot be done. Okay? So ensure that it does not matter. If you have static indeterminacy in support reactions, you can remove some support reactions and take them as redundants. Okay? If you do not have redundants, for example, if you looked at the truss structure that I had a hinge at one end and a roller at one end. I cannot remove a support reaction without making the structure unstable. So therefore, in that particular case, I had to take redundant forces which were internal. Okay? In the frame case that I considered, I could remove the roller support and still have a stable structure, and so therefore I removed the cable support. Is that clear? So this is overall the concept, that you remove the redundant forces such that you get, you identify redundant forces such that you get a stable, statically determinate base structure by taking redundant forces equal to 0. Okay? Second, what you do is you find the member deformations under loading. So how do you find out member deformations? The way you find out the member deformations if you have a loading is that you find out the loads, member forces due to by solving the statically determinate problem, and you find out the member forces, and based on that, once you know the member forces, for example, if it's axial force, if it's a truss member, it's axial force, the axial deformation is given by PL upon EA. That's the axial deformation. If you look at flexure, then the flexural deformation is given by M upon EI. So these are the member deformations that you find out under the loading. If it is a temperature loading or a lack of fit, then you know the member deformation directly. Okay? So that is the overall. Third, find member forces due to unit redundant forces. So if you have two redundants, you will apply one redundant first and put the other redundant equal to 0. So you put x1 equal to 1 and x2 equal to 0, and then you create another, find out another member forces, finding out putting x1 equal to 0 and x2 equal to 1. Okay? So find the member forces. This helps you to essentially find deflections corresponding to redundant forces using virtual work. So once you find the deflections, this we've already done, then the next step is 5 is compatibility conditions. Apply compatibility conditions, and from that solve for the redundant forces. And 7, knowing redundant forces, find internal forces and support reactions. This is your structural analysis. Okay, so I have essentially laid out the procedure for using the force method. I hope at the end of this lecture you are confident in using the force method to solve any truss or beam frame problem. Next time onwards, I am going to start with looking at the matrix approach to the force method. In this way, I am going to be introducing you to the matrix methods that are actually used in structural analysis of real structures. Thank you.